All right, so welcome back to virtual class number 1. So for the first problem, we have to use power series method to give the general solution to second derivative of y plus 4x times the function is equal to 0. Okay, and since the coefficient functions in front of the second derivative and in front of y are both analytic, we can assume that we have a solution. Y is equal to sum, so it's a power series. All right, and now what we do is we're going to find the recurrence relation amongst the coefficients using this differential equation, and then get two hopefully linearly independent solutions. Okay, so what do we know? Well, the second derivative of y, so this is now the sum. I guess I'll sum from 0 to infinity. In class, I summed from 2 to infinity, but of course this doesn't matter because m and m minus 1, when I plug in 0 and 1, will give 0. Okay, so we have x to the m minus 2, and then we get the sum from 0 to infinity 4 am, and then since there's an x term here, instead of x to the m, we get x to the m plus 1 is equal to 0. Okay, so now we look at the first term of our series, or the bottom coefficient for x to the m. And so the first non-trivial term comes up with x0, so the x0 term, which will just come from this power series, because in this one, all the terms, or the coefficients, are powers of x, which is greater than 0. So the x0 term comes from a2 and in the first sum. So we get 2 times 1 times a2 must be equal to 0. And therefore, a2 must equal to 0. Okay? Now, a0 and a1 are going to be completely free. Okay? And from this, we can set up our recurrence relation to figure out from a0 and a1 all the future coefficients. The fact that a2 is equal to 0 is going to imply that further terms will also equal 0. Okay, and we'll see that soon. So to get the recurrence relation, we need to equate the coefficients. Okay, so let me just make this. Let's look at the x to the m plus 1 terms for m greater than 0, or is that greater than or equal to 0? Everything else is, the only other thing is the x0 term. That's what we're missing, but we already figured that out. So what we get is, if I look at the coefficient in front of x to the m minus 2 coming from here, the contribution is m plus 3. Okay, so we needed to boost this m minus 2 up to m plus 1. So we get m plus 3, m plus 2, am plus 3, x to the m plus 1. Yeah, that's what we see for x to the m plus 1 from the first series. And the second series just gives us 4am x to the m plus 1. We know that this has to equal 0. So our recurrence relation is am plus 3 is equal to minus 4am over m plus 3, m plus 2. Okay, so in particular, we have that a2 is equal to a5 is equal to a8, and so on are all equal to 0. Okay, so we get this from the x to the 0 term, and then our recurrence relation gives us these zeros from then on. So maybe I'll write the general solution in this way. So I'll write the general solution is y equals a0, y0 plus a1, y1. So y0 comes from setting, this comes from setting a0 to be 1 and a1 to be 0. y1 comes from setting a0 equals 0 and a1 equals 1. So I'll write down just the first few terms from this. So this is, so y0 is equal to 1, and then we have minus 4 over 3 times 2, x cubed. Okay, so we have to jump up to x cubed because we're already looking at a3. Then we have plus 16 x to the 6th over 6 times 5 times 3 times 2, and so on. So next one, 64 x to the 9th over 9 times 8 times 6 times 5 times 3 times 2, and so on. And y1, we get that that is equal to x minus 4x to the 4th over 4 times 3, 16 x to the 7th over 7 times 6 times 4 times 3. I guess I'll do one more, 64x to the 10th over 10 times 9 times 7 times 6 times 4 times 3. Okay, so for the test it's fine if you leave it general solution in this form without giving the complete formula for the x to the m term. In this case, you can, the way to write it would be for, so let's see, so for y0, so we're looking at x to the 3k, so we're getting 4 to the k, x to the 3k, and then it's 3k, and there's no real better way to write it, 3k, 3 minus 1, 3k minus 3, 3k minus 4, all the way down to 3 times 2. Okay? And you get something similar for the coefficients for y1. Okay, so that is problem number 1. Okay, so for problem number 2, we have to use power series method again, okay, to solve, or again to give general solution for the second derivative plus x times the first derivative plus y is equal to 0. Maybe I'll mention one thing, just we gave the general solution here, okay. It's also easy to find, if I said I wanted a solution with, say, y of 0 is a and y prime of 0 is b, okay, it's just a matter of choosing the right coefficients or the right constants for a0 and a1 to satisfy whatever initial value solution we can find. Okay, so you can find general solutions. If I ask you to find initial solution, this is also simple once you have the general solution. Oh, and one more thing. You can pretend to check your work, or you can check your work just by taking, so in this case, let's see, can I zoom all the way back? So in this case we have, I'm looking at the second derivative plus 4x times the first derivative is equal to 0. Well, you could at least check the first two terms to see if you're right. So if I take the second derivative of this, the 3 will cancel, and the 2, there's the 3 and 2 that will cancel here. So I'll just end up with 4x, which is luckily 4x times 1, okay, which is coming from the coefficient there. So, you can always check the first couple of terms to see if you're getting the right solution. All right, so for the second one, this will be similar, but now we have 3 terms here. Again, we can apply power series method. Okay. And what we'll get is that we get the sum from m minus 1 am x to the m. Then we get just x times this, so we're getting m times this coefficient x to the m. Okay, so I'm not x to the m minus 1 because I have an x there. And then another sum, am x to the m, and this has to be 0. Oops, sorry, and this should be m minus 2, not m. Okay, very good. Okay, so now, well, luckily for us, these two have the same x to the m term, so we can combine the series, and then we'll get our recurrence relation in the same way as the last problem. So I'll rewrite this. So we get m times m minus 1 x to the m minus 2, and just m plus 1 am x to the m is equal to 0. Okay, so now in this case, there's, both series will contribute to every single coefficient. So every x to the m term will have a contribution from both series. So we can just write down immediately what the recurrence relation has to be. So in this case, I'm looking at x to the m, so this will become m plus 2. So I'm looking here, m plus 2, m plus 1, a to the m plus 2, plus m plus 1, am. This is all times x to the m is equal to 0. So therefore I get, so let's see, so the m plus 1s are going to cancel, and I just get am plus 2 is equal to minus am over m plus 2. Okay, so now again, I'll write my general solution. So a0 and a1 are free. Okay. And I can write y is again a0 y0 plus a1 y1. Same coefficients, so we're setting a0 to be 1 and a1 to be 0 for y0, and vice versa for y1. Okay, so we get where y0 is equal to 1. Okay, and then remember now we're setting a1 to be 0 for y0, and then the recurrence relation is going to guarantee that every single odd term for y0 is going to be 0. Okay, just because we set a1 to be equal to 0. Okay, so we have 1, and then we get minus x squared over 2. Then we get x to the 4th over 4 times 2. Plus x to the, that's minus x to the 6th over 6 times 4 times 2, and so on. And y1 is equal to x minus x cubed over 3. Again, the even terms here, since we set a0 to be 0, a2, a4, and a6 are all going to be 0. Then we get a5 over 5 times 3. Oops, same mistake. Minus x to the 7th over 7 times 5 times 3, and so on. Okay, again, for the test, this here is perfectly good general solution. Now we will want to use the ratio. Now for the second part of the problem, we have to use the ratio test to show this is valid for all x. Okay, so that requires, well, it's helpful to be able to, have the formula for the x to the m term if you're going to use the ratio test, because you're looking at something like am plus 1 over am. Notice we have to be a little careful here when applying the ratio test to y0 and y1, because if you're doing the ratio test, we're looking at consecutive terms, and in both because of our choices, we have that both terms, the consecutive terms are alternating 0, so we're either 0 or something dividing by 0, which isn't so nice, but there's a trick to get around this, which is useful. So maybe I'll say this: if we write y0 of x is equal to 1 minus x squared over 2 plus x to the 4th, 2, and so on. Okay, then this is really, y0 of x is really, I'll say y0 prime of x squared, where y0 prime is exactly this, but just all the coefficients have been divided by 2. Okay, so we have 1 minus x over 2 plus x squared over 4 minus 2, x cubed over 6 times 4 times 2. Sorry, I should put that there. And so on. Okay. So notice all that we've done is if I plug in x squared into this function, then I get exactly my original solution. And now, well, it's true that if a power series, is valid for all x, then it's also valid for all x squared. Okay, so this, these terms where all the terms are even, or in general for where you're jumping up by the same multiple every time, well, you can view that as plugging in some power of x into a different power series. Now, if the radius of convergence, say of y0 prime, was finite, if this is only valid for, say, x less than r, okay, well then y0 of x would be valid for, x less than the square root of r. So you do have to be careful when you're doing this if the radius of convergence is finite, because, when you square something, it does change what the values of this function can be. On the other hand, if this is valid for all x and r is infinity, then this one will be as well. Okay? So let me just, for y0 prime, what we're getting is that the difference in the coefficients, we have am plus 1 over am, well, this is just equal to 1 over 2m. Okay? And since this is going to 0, as m goes to infinity, this implies the radius of convergence is valid is equal to infinity. So r is equal to infinity, or in other words, it's valid for all x. A similar argument, maybe I'll just write this. Well, so for y1, what you can first do is write it as x times something in terms of, well, something with only even coefficients. So we have 5 times 3, let's see, minus x to the 6th over 7 times 5 times 3. And so on. Again, this will be now, you can write this as a square. Okay, so I won't write all this out. It's 1 minus x over 3, but you're plugging in x squared into this. Again, the ratio test will imply that this, the difference will go to, or the ratio will go to 0, so it's valid for all x. And then since this is valid for all x, if I plug in the square, it's valid for all x. And if I multiply by x, it's valid for all x. Okay, and finally, we want to find a unique solution. So y of 0 is equal to 1. The derivative at 0 is equal to 0. Well, in this case, we got lucky, and this is just the function y naught. Okay? In general, because exactly this is where the derivative comes from, so this is y prime of 0, or, when I plug in for 0, and then this will be, give me y of 0. Okay, so I set a naught to be 1, and a1 to be 0 for y naught. Okay, so on to problem 3. Okay. So now we need to use method of Frobenius in order to solve x times second derivative of y plus 2 times the first derivative minus xy is equal to 0. Okay? So here we have to be, first, if we want to use the method of Frobenius, we should check that this fits into, or that x equals 0 is a regular singular point. If I divide by x, I'm getting second derivative plus 2 over x times the first derivative minus y is equal to 0. And luckily for us, well, this is not analytic, not even defined to x equals 0, but, x times 2 of x is. Okay, and this is perfectly, the y coefficient is perfectly fine since it's constant. Okay, so we can apply method of Frobenius. It gives us a solution of the form am x to the m plus r. All right, so plug in into this, plug this into the differential equation, see what we get. All right, so the first term is m plus r minus 1, am, and then it's x to the m plus r minus 1, right? Since we had originally, or I guess we're multiplying the second derivative by x, okay, so we get, instead of minus 2, then we get plus the sum, so m plus r times the sum, am x to the m plus r minus 1. Oops, sorry, there's a 2 there. And then minus, now we have x times y, so we get am x to the m plus r plus 1. Okay, so all of these are going from 0 to infinity. All right, and we know that that is equal 0. Okay, so first we have to figure out the smallest, or figure out r from the smallest coefficient. I could have done this just by putting this into some standard form and reading off the indicial equation that way, but let's just do it by looking at the smallest term. So I get contributions from just the first two series here. So in particular, I get, so this is where m equals 0, so I'm getting r times r minus 1, a naught, which I'm assuming that a naught is not 0, plus 2r is equal to 0. Okay, so therefore I get r times r plus 1 is equal to 0. Oh, sorry, there's an a naught here as well. So r is 0 and minus 1. Okay, so I have to be a little worried now because I have a power series solution, or I have my roots. So I get one power series solution, but my second one is differing by an integer. Okay, so let's just hope at this point that that's not a worry. Okay, and again, if you have, anytime you have two roots, you always go for the largest one because you know that that's the solution. Okay? All right, so here, again, now there's actually another step for this problem, because instead there's an x to the r minus 1 term, there's also an x to the r term, which only gets contribution from the first two series. So in this case, it's r plus 1 times r times a1, plus 2r, sorry, our 2 1 plus r, a1, is equal to 0. Okay? Well, in this case, so we get r squared plus 3r plus 2 times a1 is equal to 0. So in other words, r plus 1 times r plus 2 is equal to 0. Okay, so notice that for, say, r being 0, okay, which we're going to assume, we're going to apply or try to solve for the largest of the r values first. What this tells us is that a1 has to be equal to 0. Okay, and hopefully in our recurrence relation, this will imply a lot of other terms are also equal to 0. Okay, so let's see what we get in the recurrence relation. So now we're going to look at the x to the m plus r plus 1. I could set r to be 0, but I'll do it generally here. Okay, so now you want to look at the x to the m plus r plus 1 term. The contribution from the first series is m plus r plus 2 times m plus r plus 1, a m plus 2. Okay, that's what you get because this coefficient is shifted by 2. The second one is 2 times m plus r plus 2, am plus 2, and then the last one is just minus am. Okay, and set this equal to 0. All right, so now this isn't too terrible, since we can write this as am plus 2 is equal to am over, let's see, m plus r plus 2, so I can pull that out. And then we have m plus r plus 3. Okay, so now I feel comfortable in setting r equal to 0, okay, to get one solution. So notice that a1 has to be equal to 0, and therefore by this recurrence relation I'm going to have that a3, a5, and so on are all equal to 0. So I get am plus 2 is equal to am over m plus 2 m plus 3. Oops, let me put that here. All right, and now since I'm assuming r equals 0, our solution, well, it's going to be a naught times 1, and then I get plus. So here, I'll write out the first couple of terms. Here, it's easy enough to write down the general formula. When I'm getting a2, so I'm getting x squared over 2 times 3. The next term is a to the 4th, and then if I look at this is for m equals 2, so I'm dividing by 4 plus 5. So I'm getting 2 times 3 times 4 times 5, and so on. And actually what it is just x to the 2m divided by 2m plus 1 factorial. Okay, so that's your first solution. And now you have to look at r equals minus 1, okay? And here it turns out that we get lucky, right? Because if you look, the same exact recurrence relation is going to be valid. You know, we've done the work, just at this point we plugged in r. So now we get am plus 2 is equal to am, where r is now minus 1, so we get m plus 1 times m plus 2. But this is completely valid for all values of m, right? So we're never dividing by 0, doing anything a little funky like that, okay? So the general solution now, or the solution for r equals minus 1, a constant. So again, maybe I'll just call this a naught, okay? And then we have a 1 over x, okay? Because remember, our general solution is of the form it looks like x to the r sum am x to the m. Okay, so I have this 1 over x in front. And then I get 1 plus x squared over now, so m is 2, so this is 2 times 1 plus x to the 4th over 4 times 3 times 2 times 1. And generally, I'm getting x to the 2m over 2m factorial. Okay? Or another way that I could write this is now it's, again, a constant, or maybe I'll put a naught prime just to indicate that these don't have to be, these are just random real numbers. They don't have to have any relation. So I get 1 over x plus x over 2 plus x cubed over 4 factorial up to x to the 2m minus 1 over 2m factorial. Okay, so that's the general solution. Or sums of these two functions is the general solution. So notice here, there's a little something that's got a little funny at some point. Because I assumed in my x to the r term, or I obtained that a1 has to be 0 because, a1 times a positive number is equal to 0. This isn't true for r equals, if r is -1, then all of a sudden I don't have to assume that a1 is equal to 0. It could be some other value. On the other hand, I'm getting a valid solution assuming that a1 is equal to 0, so, you might as well do it, okay? So even if it's not something that's, forced upon you, as it is for the first solution, generally, if you can, assume that it's 0 and get a simpler answer, well, then you should do it, okay? So, in fact, maybe I'll just mention, so the general solution here, so this is, it turns out that the first solution is nothing more than sinh of x over x, and the second solution is nothing more than cosh of x over x. Okay, for the exam, not something that you need to know, and actually I'll give you these common series formulas, but in this case you do get a nice answer. Okay, so on to problem 4. Okay. So we have x squared plus x, second derivative of y plus 4x plus 2 times the first derivative plus 2y is equal to 0. Okay. Again, you can check that x equals 0 is going to be a regular singular point. Okay, so this is just x times x plus 1. Okay, so dividing by that will give you that both 4x plus 2 divided by x plus 1 and 2 divided by x plus 1 are analytic at x equals 0. Okay, so again, we are guaranteed a solution of the form y is the sum of x to the m plus r, amx to the m plus r. So we just have to plug in. Unfortunately, now we get 5 series. Okay, on the test you probably won't get 5 series, but I thought for, make the test review problems harder than the test problems. Okay, so what do we get? Well, it's not too bad. So we end up with m plus r, or not too bad, I guess, because we've just done a lot of these. So our first term is x squared times the second derivative, which gives us just x to the m plus r. Our second term is x times the derivative, or second derivative. So we get x to the m plus r minus 1. Then we end up with 4 times m plus r x to the m plus r. Okay, so that's coming from the 4x times the second derivative. Then the second, again, that has an m plus r am x to the m plus r minus 1. Okay, so that's coming from the 2 times the derivative. And finally, we get plus the sum of 2am x to the m plus r is equal to 0. Okay? So now, what are our smallest terms? Well, the smallest coefficient will be x to the r minus 1 coming from the second and fourth series. That's where m equals 0. So what we end up with is r times r minus 1 plus 2r, okay, is equal to 0. So in other words, we get r squared plus r, and again we end up with r equals 0 and negative 1 as a solution, or as possible values of r. And again, we know that r equals 0 is going to work because that's the larger root. Okay? So let's try to do some combining here so we can get something which looks a little nicer. So if we look at the x to the m plus r term, okay, well, we have a contribution in the first series of m plus r times m plus r minus 1. The second series is shifted, right? So it has to be, you have to plug in, instead of m, you have to plug in m plus 1. So this is times am. The second term is m plus r plus 1, m plus r, am plus 1. Then we have plus 4 times m plus r am. Then we have another shift, so we get 2 times m plus r plus 1 am plus r plus 1. And finally, for the last one, we just get 2 am. Okay? So we know that this is equal to 0. And hopefully this simplifies. Okay? So let's see. So we can pull out an am. Well, let me just do maybe the am plus 1 first. And sorry, I realize this is not an m plus r plus 1. That is just an m plus 1. So you end up with am plus 1 times m plus r plus 1. And then you see we have an m plus r here and a 2 here. So we just get m plus r plus 2. Okay? Now on the other hand, for am, we're getting plus am. Now here I have an m plus r, which I can pull out for the first two terms. So I get m plus r, and then m plus r plus 3, okay, and then plus 2. Okay, and this is all multiplied by am, so I get that am plus 1 is equal to a minus am times m plus r plus 3 plus 2, all divided by m plus r plus 1 times m plus r plus 2. And then a nice algebraic miracle happens where it turns out these are exactly the same. So we just end up with am plus 1 is equal to minus am. Okay, so why is this? Well, maybe it's easier if you just set x equal to m plus r. Okay? Then notice the top is x times x plus 3 plus 2, x squared plus 3x plus 2, which is x plus 2 times x plus 1, and that's exactly what the denominator is. Okay, so they turn out to be equal. So what this means is that we have a very simple recurrence relation. In particular, our solution for r equals 0, okay, is going to be, well, it's going to be a naught times 1 minus x plus x squared minus x cubed, and so on, okay, which is precisely a naught divided by 1 plus x. Okay, so that's the geometric series where you plug in minus x. And so notice that this is valid for the absolute value of x being less than 1, which should not be too surprising here, because x squared, this is plus x, is really x times x plus 1, so x equals minus 1 is the other singular point, and our solution can't extend past that. Okay? Okay, so now let's think about the r equals minus 1 case, because there's a nice little trick here. Okay, so notice our recurrence relation, even though it cancels, so you think that it's exactly the same recurrence relation as before, it's of a slightly different flavor, so I'm just adding an equals 0 here. So it's a different flavor because some of these terms are 0. So in particular, if I plug in minus 1, I'll end up with 0 over 0. Right? So it's not exactly the same as something nice like 1 over 1, say. Okay, so and actually something kind of nice happens. So let's look at the a1 term, okay? So I know a naught has to, say, not be 0. So for a1, I get that this, and now I'm plugging in r equals minus 1 into this equation, so I get a1 times 0 times, I guess 3, that doesn't, oh, or 1, though it doesn't really matter, plus a naught times minus 1 times 2 plus 2 is equal to 0. Okay? And now for every other coefficient, right, you're going to have a perfectly fine solution in the sense that you'll never be having 0 over 0, right? So the only situation is this one when m equals 0 and r is equal to minus 1. But now something kind of nice happens. So first, notice that a1 can be arbitrary. A naught must be 1, right? Because otherwise I would have no chance of having this set equal to 0. But then what I can do is I can set a naught to be 1, which is fine. a1, it's arbitrary, and I just need one other solution, so I might as well set it equal to 0. And then this implies by my recurrence relation that a2 is equal to a3. They're all just equal to 0. Okay, and I'm getting r is minus 1 here. So my solution is just 1 over x. Okay, so the general solution is a over x plus b over 1 plus x. Okay, so you might be, well within your right to say this is some, trickery that's going on here. Like, why'd I just set a1 equaling to 0? Well, notice actually the general solution that you would get from this is it would be x to the r, so it would be 1 over x, times 1, and then I just make a1 arbitrary, so this would be plus a1x, so minus a1x squared, and so on. Okay. But this fits exactly into our general solution. Since I'm dividing by 1 over x, this is 1 over x plus a1 times 1 minus x squared plus, 1 minus x plus x squared minus x cubed, and so on. Okay, which is again just 1 over x plus a1 times 1 plus x. Okay, so you would think, so I set a1 equals 0 just to get something nice. Whatever you set a1 to be, you'll still get a general solution. Okay, another way you can do this, so you can also use this reduction of order would work here. Okay, it gives you kind of a more systematic solution. Okay, but in this case, we just notice that the recurrence relation actually works. Okay, except you have some sort of funny condition where you know what a naught has to be, and then all the other terms are determined. Okay, but in any case, that's the. That's not. This is the general solution for part 4. All right, so now on to problem 5. All right, where we had the differential equation x squared times the second derivative of y plus x times the second derivative of y plus a quarter x minus v squared y is equal to 0. Okay, so this is close to a Bessel function, except that this term is missing an x squared, and there's a quarter out in front. Okay, so hopefully if we make this change of variables, we want to change, I'll just write change, so we write square root of x is equal to z, and we're going to write this differential equation now in terms of z. Hopefully we get just to the Bessel equation. Okay, this turns out to be quite common if you have a lot of differential equations. There's a lot of these second order ODEs can be reduced to Bessel equation if you're clever with your change of variables. Okay, so what do we have? So we have z is the square root of x. Okay, so I'll just write x is z squared. We also will want to write dy dx and the second derivative of y with respect to x in terms of something involving z. Okay, so and then that will be the equation that we then solve. Okay, so dy dx we know is equal to dy dz dx. Okay, so the dy dz we leave alone because that's going to be the derivative for our new equation, and for dz dx we just get 1 over 2 square root of x, and it's convenient to put that in completely in terms of z, so it's just 1 over 2z. Okay. The second derivative is similar. Okay, so you take dx squared. So this is the derivative with respect to z of dy dx, times dz dx. Oops, oh my gosh, I can't write my x's in the denominator. Okay? So this is the standard way to substitute for the second derivative, or one of the standard ways, and luckily we've already put dy dx in terms of something involving z, so I can take the derivative with respect to z. Okay, so what is this? Well, it's the derivative of this product, so I get dy squared dz squared 1 over 2z plus dy dz times the derivative of 1 over 2z, so I get minus 1 over 2z squared, and this is all multiplied by dz dx, okay, which we worked out is just 1 over 2z. Okay, so I end up with the second derivative of y with respect to z times 1 over 4z squared, and I'll write minus the derivative of y with respect to z times 1 over 4z cubed. Okay? And now we're just going to plug in both of these expressions in for here and also make the change that x is equal to z squared. Okay, so x is z squared, so x squared is z to the fourth. Then I get the second derivative of y with respect to x squared. Put that in for z, so I'm getting, maybe I'll just, I'll include it like this. D squared y dz squared, 1 over 4z squared, minus dy dz 1 over 4z cubed. Then we have x, which is z squared, dy dx, which is dy dz 1 over 2z. And finally here we just have a fourth. And now kind of the whole point, or the reason that you might suspect that square root of x is a good thing to substitute in is because we have an x here, which is now turned into z squared minus v squared y is equal to 0. Okay? And luckily this should reduce to something nice. So here the second derivative term just becomes a quarter z squared. And now I'm just going to write y double prime. Okay, but now this is the second derivative with respect to z. Now if I look at the derivative, so here I'm getting a 1/4 minus a quarter z, and here I'm getting plus a half z. Okay, so I get 1/4 z dy dz, okay, which I'm going to write as y prime. Okay, so that's coming from this expression added to this expression times the z fourth, plus a quarter z squared minus v squared y is equal to 0. And now I can just turn this into, by multiplying everything by 4, the standard Bessel equation with the same parameter. Okay? So sometimes when you do these substitutions, you end up, maybe you get to a Bessel equation, but the Bessel equation is of a different parameter than what you started with. Here you end up just getting the same thing. Okay, so therefore we know the general solution is jv of x plus, or a jv of x plus b j minus v of x for v not an integer. Or you could say if v is an integer, then we should have a jv of x plus b y minus v of x. Okay? So that's the general solution for that Bessel equation. Okay, so that's it. I will conclude here.